Now that you have rejected the bad channels from your dataset, you will want to correct the motion artifacts in the channels you kept. You may wonder which motion correction technique to use among the ones offered by Satori. In this video, we will describe each method and indicate in which cases they are recommended and in which they are not. First, we'll talk about spike removal. To do so, we'll open Analysis here in the top left, and then NIRx Data Preprocessing, and then click Advanced, and here's spike removal. Spike removal allows you to detect large peaks or spikes in your data and replace the time samples detected as spike by interpolated values. Basically, each channel data will be inspected in small pieces of a predefined length. Within each piece of signal, the values above the threshold will be marked and replaced by a new value computed from the unmarked samples of the data piece. This operation is repeated several times to smooth the data. There are 4 parameters you can specify. The first is the threshold value to consider a data point as a spike, right here. The second is the lag of the sliding window, here. The third is the number of iterations, and the fourth is the influence or weight you want to give to the interpolated values in your data. The threshold value is specified in z-score units, which means that values above or below z standard deviations from the moving average or the mean of the sliding window will be marked as a spike. An important thing to mention is that at each iteration, the sliding window's mean and standard deviation, in other words, the spike's threshold, will be different. This is because at each iteration, spikes are replaced by interpolated smaller values. As a result, each iteration will detect smaller spikes. This is very useful in removing spike edges that might not be detected as part of a spike from the first iteration. You can look at the video on normalization for more info on data to z-score transformations. The influence value is the weight you want to give to the interpolated value when computing the mean and standard deviation of the following iterations. This value should be between 0 and 1, which means that at the following iterations, interpolated values will not be used to compute the mean and standard deviation of the sliding window. An influence of 1 means that the interpolated values will be included in the mean just as the other values of the windows. The noisier your data, the closer to 1 the influence should be. The lag is the length of data pieces you want to look at to detect spikes. The more stationary your data, the more lag you should include. To detect spikes correctly, you need a good estimate of the true mean and standard deviation. If your sliding window contains too many spikes, the mean and standard deviation will be inflated and you won't detect sufficient values. So, the noisier your data, the shorter the lag should be. The lag should be a bit more than the duration of a spike. The more stable your data, the more time you can include in the lag without including new spikes. Finally, I'll discuss iterations. The noisier your data, the more iterations you should have. This is because the first iteration will remove the largest spikes and the following ones will remove increasingly smaller spikes. For the interpolation method, we recommend that you try each of them to see which gives the best results for your dataset. The next method for artifact removal available in Satori is TDDR, right here, which stands for Temporal Derivative Distribution Repair. The good thing about this method is that it doesn't require the specification of any parameters and works well for both spikes and baseline shifts. Basically, this method splits the data into high and low frequencies, applies motion correction on low frequency components, below 0.5 Hz, by estimating the temporal derivative, which is the variation of the data over time, and correcting it, and lastly, it adds the corrected low frequency component back to the high frequency component. The last method available in Satori for motion artifact correction is CBSI, right here, which stands for Correlation-Based Signal Improvement. CBSI relies on the assumption that oxygenated and deoxygenated hemoglobin signals should be negatively correlated. If they are correlated, it is due to motion artifacts because optode motion has the same impact on all signals and affects the recording in general. Basically, the deoxygenated signal is scaled to the same variance of the oxygenated signal and then subtracted from the oxygenated signal. The rationale is that positively correlated features of the signal, such as motion, will be negated by the subtraction and therefore removed from the data, while negatively correlated features, for example hemodynamics, will sum and remain in the data. A good thing about this method is that you don't need to specify parameters.